Welcome to Lecture 2B. Title is Limits and Existence of a Limit. And so this is the second lecture in a series of 3 for Lecture 2. Material for this particular lecture can be found in Chapter 15.2 of the textbook. Objectives are determining the existence or non-existence of a limit for a multivariable function and illustrate methods used to determine if the limit exists for two variable problems. So the focus on there is on using tools to determine if the limit exists in this particular lecture. Concepts and definitions. Methods for converting a problematic function into rational functions for which the existence or non-existence of a limit is easier to prove. And there are 3 approaches that we can typically take. One is to factor the numerator, second is algebraic conjugate method, and the third is change of variables. We'll discuss examples of each one of these 3 cases. So as usual, the second slide is just an outline of the material to follow in this lecture, and there are just 9 items here. You can just quickly scroll through them to basically see the material that's coming in the next couple of slides. All right, so first of all, we're going to start with some basic limit laws. And there are 2 theorems here that we consider. One is the limits of constant and linear functions. And the second theorem is limits of 2 variables. Okay, so these can be proven using the delta epsilon method. We're just going to state them as they are. So there is one for constant function, determining the limit for a linear function in x and a linear function in y. And then there are various operations that you can perform on functions. So for instance, sum, difference, constant, multiple, product, quotient, power, and root. And basically it's saying that if you can show that the limit of one function exists and a limit of a second function exists, then the operation on those 2 functions will provide a new function whose limit also exists. So these basically again can be proven using delta epsilon method. And typically we will not basically go into the details of proving these things. It'll just be understood that for polynomials, rationals, and algebraic functions in 2 variables, right, we know that the limits exist so long as you're within the domain of the function. So again, these are basically just the particular laws that we'll be making use of. Okay, so let's take the basic limit laws, which is a direct proof example. So basically it's saying if this and that exists, then the outcome exists. So we're going to take the function here, z is equal to 3x squared y plus square root of xy. And we're interested in knowing whether or not the limit exists as x and y approaches 2,8. Now for this particular function, we need to know the domain and the range. The domain is limited because of the square root. So as long as the product of xy is greater than or equal to 0, then essentially all other values of x and y are admissible. The range in this case you can show can be any element of the real number set. Now if we were to plot this domain that is on the xy plane, you'll notice that the domain will include all possible combinations of x and y in the first and third quadrant, including the x-axis and the y-axis. That's why I've shown it as a solid blue line, because it's basically a closed set. All right, so how would we go about proving this particular function's limit existence? We basically start by making use of all the specific limit laws that we discussed in the previous page. And so let's start with x squared. Well, we know that basically by law 6, the limit of this exists. Then we look at x squared y. Well, the limit of this exists by the product law. Then we multiply by 3, and we find that the limit exists because of the constant multiple law. Then we move to the second term. xy, the limit exists because of the product law. The square root of xy exists because of the 1 over n root law. And finally, we add the 2 functions together, and basically the limit exists because of the sum law. So effectively, this is the sort of procedure used to prove the limit exists. You could have done it in a different sequence of steps, which is fine. We're not going to ask you to go through this procedure every single time when you see rational functions. This just shows you how it would have been done on a relatively simple problem. All right, so let's look at then the second case, which is a factoring of the numerator. Again, it's a direct proof example. There is an interactive diagram on the next slide, just so that you know that you've got something you can actually play with and try to understand graphically what it looks like. You're given that the function z is x squared minus y squared over x minus y, and you're interested in determining what the limit is as xy approaches 4, 4. Now, always look at the denominator, because that's already a telltale sign that we might be in trouble. And sure enough, the xy 4, 4 would give you a denominator of 0, which means we have a problem. And so we call 4, 4 as a boundary point. In other words, we can't really get onto this point or series of points, since x and y can take on combinations of values. So in this case, the domain would be all x and y except x equals y. And the range in this case would be all values of z. You can show that to be the case, because the numerator can be positive or negative depending on the value of x with respect to value of y. Okay, so in using the factoring numerator approach, we need to take the numerator and just factor. It's a quadratic equation. And so x squared minus y squared is similar to x plus y times x minus y, divided by x minus y. Well, the x minus y on the numerator and denominator factor out, and you end up with final solution of x plus y. Now, the limit of that function exists, again, according to the sum law, because if the limit x exists, it does, and the limit y exists, it does, then the limit of the sums also exists. So you can just more or less substitute the value for x in and the value of y, and you'll end up with a value of 8. All right, so this is the interactive diagram I mentioned you can play with. Notice again that y equals x is excluded from the graph because x equals y is not part of the domain of the function. Anyways, look at this particular interactive diagram to help you visualize the problem. All right, let's look at this function again in a little bit more detail. We want to basically determine what that line is and also graph what the domain looks like. So if we take the final result that we obtained, that z was equal to x and y, x plus y, then if we want a line, then we need to basically parameterize. So for instance, we could choose x to be t, and that y would therefore be t because it's and then the sum of the two would just be 2t. And t is an element of R, right? So that basically would be the equation of line. You can also write it in position vector form, in which case we would just angle bracket x component t, y component t, z component 2t. So this is basically the position vector that you would see. In the xy domain, you can see the domain. The line y of x, which is a dotted blue line, is not part of the domain. So it's everything else basically is part of the domain. This is just an illustration for this particular problem, and just trying to graph as much as possible. All right, so let's consider a second possibility, and that is of a direct example. That's algebraic conjugate method. So you're given a function here. Z is the limit as x and y approaches 0.41 of the function that's shown there, xy minus 4y squared divided by square root of x minus 2 square root of y. Now notice that the 0.41, if you plug in the values in the denominator, gives you 0, which is undefined, and as a result, the 0.41 is a boundary point. So first thing we want to do is to determine the domain of the function followed by its range. Well, clearly, it's the domain basically involves the denominator not being equal to 0, and so you can see that square root of x minus 2 square root of y must not equal 0. Also, because of the square root symbol, the values of x and y should be greater than or equal to 0. And therefore, as far as a plot is concerned, It's only the first quadrant that applies as far as the domain is concerned. And also the line, which is shown in red on the right, that is over here. This line basically is nothing more than x equals 4y. That is, you can take this expression and simplify it and make it look like this. That means that the red line and the black dot lying on that line, are excluded from the domain. So if you're basically going to compute the limit, then you have to approach the point on this line from all possible directions. However, you cannot come along the line because the line is not in the domain. And so you can approach from below or you can approach from above, but that's all you can do. So that's the basic picture. That's the setup that we have to begin with. All right, so now we can go ahead and compute the solution. And so an algebraic conjugate method means that we take a look at the denominator and we realize that if we multiply top and bottom by the conjugate of the denominator term, that means square root of x plus 2 square root of y top and bottom. This is 1, which means it leaves the answer unchanged. However, multiplying this term here, x square root of x plus 2 square root of y, times square root of x minus 2 square root of y, gives you this term that you see here, x minus 4y. And so this term now can be further simplified because you can factor out a y in the numerator term, in which case you get a cancellation of x minus 4y that leaves you with this expression here. Now, to compute the limit here, we can basically apply laws 7, 3, 1, and 4 in that order from theorem 15.2, and basically just plug in the values to show that the limit basically is equal to 4. Again, you cannot approach along the line. You've got to approach from either above or from below. So this is the final limit that we essentially end up with. All right, we can also graph this function. So let's do that. And so I've made use of the 3D math program. You can click on it and play around with it if you want. Anyways, the blue line is basically the line in the xy plane. And then you can compute what the z value is as you move along the xy plane, and that's the red line that you see, which lies on the surface. Now, in this case, the surface is curved because the function was nonlinear. Right? So that's why you have this sort of funny looking shape. And so if we graph this out, we basically would have, you have to parameterize a line, so you would have x is some function of t. The simplest thing is just to call it t, right? You have y equals 1/4 x, so if x is t, then y becomes 1/4 t. And then substituting for x and y into the original function, you can get z as a function of t. And that's precisely what we do in the next step here. So there's x of t equals to t, y of t is equal to 1/4 t, because it's the line we're interested in. And then substituting x and y in for the equation for z, you end up with the expression shown there. And then after some simplification, we end up with 1/2 t to the power 3/2. And t has to be greater than 0, again, because of constraints on x and y. If you want to put this in a position vector form, Matt, then basically you take the x, y, and z components in parameterized form and put them in an angular bracket. So the position vector basically is a vector that points from the origin to every point along the line on the surface. All right, so let's look at another direct example involving changing of variables. And the question is, determine if the limit z equals the limit of x or y approaching the point 0, 0 of x squared y over x squared plus y squared exists, and if so, compute its value. All right, so the solution involves 4 steps. We'll notice here that 0, 0 basically makes the denominator equal to 0, which means that the function is undefined. Hence, the point 0, 0 is a boundary point. So that the first step is to establish if it's a boundary point or not. The next step is to essentially do a change of variables. So what we would like to do is to express x in terms of 2 new variables u and v, and y in terms of 2 new variables u and v, the same 2 variables. And the most common 2 variable transformation, if you see an expression that involves x squared plus y squared, is to basically let x be equal to v cos u and y to be equal to v sine u. And there are some restrictions placed on v and u. V is greater than or equal to 0, and u lies between 0 and 2 pi. And the reason we do that basically is to ensure that we have a system whereby we have a mapping that is one-to-one and onto. And so for every point that's x and y, there's a unique combination of u and v. So that basically is the situation. So we're going to be using this. And the other thing we'll make a note of basically is that we need to figure out what the mapping is between x, y of 0, 0 is, and the corresponding values in the UV plane. So first step would be, which is item 3, is to substitute for x, which is v equals u, and y equals v sine u, into the original function, which is x squared y divided by x squared plus y squared. If we do that, we end up with v cubed cos squared u sine u divided by v squared. And of course, the v cubed and v squared gives cancellation, leaving only a single v in the numerator. All right, so the next thing to figure out is, well, if we're going to approach the point 0, 0 in the xy plane, what is the point that we would approach if we're looking at the UV plane? Well, in the UV plane, the value of v would approach 0, but u could take on any value. Now, if you look on the right, you'll see essentially the measurements that are taken. So, for instance, u basically would be the argument of the cos and the sine. And so u would be basically in a direction which is counterclockwise, making a full circle from 0 to 2 pi. V is along this radius, which is the length, which is this v that you see here. So this is a diagrammatic way of basically showing the relationship between x and y and u and v. All right, so the next thing to do after the simplification, we end up with the fact that the limit of v approaching 0, which would be corresponding to the origin, v cos squared u sine u will be equal to 0 for all paths. Now, why is that? Because, again, we can basically use the product law to show that the limit of v approaching some a of v cos squared u sine u exists for all values a greater than or equal to 0. And also, we can basically show that if the argument of the limit contains a multiplicative term that's v to the power n, where n is greater than 0, then the limit exists. So that corresponds to the cos squared term that you see here, and the product law basically relates to the fact that we have v cos squared u and sine u. So in this case, we have shown that the limit exists. All right, so this concludes Lecture 2B. Thank you for listening.